Lesson 3.4 continues on with zeros of polynomial functions. In this lesson, we'll utilize division and factoring as a means to find our zeros. For zeros of a polynomial function, any polynomial of degree n has up to n real solutions, or the x-intercepts, and exactly n complex solutions. Complex solutions include both real and imaginary. When we solve, we may end up with both real and imaginary solutions. Example to review. It says determine all zeros for each function. Anytime we're asked to find zeros, we're just going to set our equation equal to 0 and solve. First, we start with a linear function, and this should be pretty fast. If we set x minus 2 equal to 0, we'll add 2 to move that to the other side. And x equals 2. We have one solution, and it's a real solution. In the next example, f of x equals x squared minus 6x plus 9, we're asked to factor. Once we set it equal to 0, we can't get x by itself without factoring. Let's see. Two numbers that multiply to get positive 9 but add to get negative 6 in the middle would be negative 3 and negative 3. Notice in this example, both of those parentheses are the same. This means x will equal 3 is just one solution, but because there are two technically represented with a quadratic function, remember from before we say this is a multiplicity of 2, but it's still one real solution. For our final function, f of x equals x cubed plus 4x, this would be a cubic function, and it should have 3 complex solutions. Now, in order to solve a cubic function, we can't factor until we find, or we can't factor into parentheses until we find a common factor. X cubed and x could factor out of both of those terms, and that would give us x squared plus 4 left over. Now, x would equal 0 on the outside, but this x squared plus 4 doesn't factor any further. However, we can get x squared by itself simply by moving 4 over. If we have x squared is equal to negative 4, and we take the square root of each side, we must recall what we've talked about with quadratic functions. You can't have the negative on the inside of that square root, so we'd have to factor out the I after we put the plus or minus out in front. If we factor out the I, we know that the square root of 4 would be 2. So this is plus or minus 2i. Notice we have one real solution and 2 imaginary solutions for a total of 3. We have exactly 3 complex solutions. The rest of our lesson takes a look at finding zeros of polynomials when a factor is given. If you know or you're asked to prove that you have a factor of a polynomial, you'll verify that factor using synthetic division. Now, for our purposes, we're going to focus solely on quadratics and cubic functions. Once you verify your factor using synthetic division, you should get a quotient. That quotient will be quadratic. And we can solve our quotient either by factoring or quadratic formula. In the example, show that x plus 6 is a factor of x cubed minus 56x minus 96. Now, we worked with this in lesson 3.3. To show it's a factor, we're going to plug it in for synthetic division. Remember, if your divisor is x plus 6, that means you're verifying it crosses the x-axis at negative 6. And that's what we'll plug in for synthetic division. In order to be a factor, you must have a remainder of 0 or no remainder. So let's put that to the test. We'll put negative 6 on the outside. To draw our line for work, we'll go down and across. Looking at our polynomial, we have x cubed minus 52x minus 96. Remember, we're supposed to verify that all terms are represented. We have our x cubed term, so I'm going to put a 1 as my coefficient, but then it drops down to the x term. We're missing the x squared. This means we need 0 as a placeholder. Then our linear term, negative 52x, I know it's a pretty big number, and our constant at the end goes all the way up to negative 96. Let's verify that x plus 6 is a factor. We'll drop down that lead term. Anything below that orange line will be multiplied to the number on the left. 1 times negative 6 is negative 6, and it goes in that next column. And then we add the two numbers together. 0 plus negative 6 would just be negative 6. Multiply that to the number on the left. Negative 6 times negative 6 is positive 36. Now remember, we're technically adding, so negative 52 plus 96, wow, try that again. Negative 52 plus 36 would be negative 16. And believe it or not, negative 16 times that negative 6 out on the left-hand side is positive 96. This means we get a remainder of 0. That verifies that x plus 6 is in fact a factor. Now remember, with what's left over, we know that the number at the very right-hand side before the 0 should be our constant. And then we have our x term, we're just going to keep increasing, and x squared. So we're left over with a quotient that's quadratic. So the answer is called the quotient. Any answer in division is known as that. And that's going to be x squared minus 6x minus 16. Now it says find the remaining zeros of p of x. What that means is we now need to solve that quotient. So move that up over here. So if we solve this quotient, we're going to set it equal to 0. X squared minus 6x minus 16 equals 0. Our goal will be to either factor or apply quadratic formula if needed. If we try to factor, can you think of two numbers that multiply to equal negative 16, but add to equal negative 6? I know negative 16 could break down into 1 and 16, it could break down into 2 and 8, it could break down to 4 and 4. I think the 2 and the 8 are going to work out for us. We'll split apart our x squared into x times x. And if we use 2 and 8 as our numbers, we need to figure out how to get negative 6 when we add. If we make 8 negative and 2 positive, when we add them together, we would get the negative 6x in the middle. And when we multiply, we'd get that constant of negative 16. Now that we've factored, we'll apply that zero product property, and this is the easy step. We just set each parenthesis equal to 0 separately and solve. First, we'll add 8, and then we'll subtract 2. We first verified that x plus 6 is a factor. That was kind of our step 1 over here. And then find the remaining zeros. That's where we solved. There's our second step. So our two answers would be x equals 8 and x equals negative 2. They are the remaining zeros for p of x. In our final example, it says show that x minus 2 and x plus 3 are factors of this quartic function f of x equals 2x to the fourth plus 7x cubed minus 4x squared minus 27x minus 18. Then find the remaining zeros. Boy, do we have our work cut out for us on this one. All right, so in our step 1, it's going to be twice as big as it was in the last example because we're verifying 2 of our factors. So for step 1, we're first going to show x minus 2 is a factor, and then we'll show x plus 3. If x minus 2 is a factor, we know we're going to plug in x equals 2 and test that in synthetic division. That means the 2 goes on the outside. And looking at our quartic function f of x, we have 2x to the fourth, 7x cubed, negative 4x squared, negative 27x, and negative 18 as our constant. Notice all terms are represented from the quartic term down to the constant. So that's good. We don't have to include any zeros. We've got a 2, a 7, negative 4, negative 27, and negative 18. What I'd like you to do is show that this is verify that this is a factor using synthetic division. Don't move on to the next step though. Once you're done, press play, and we will move on to the next step together. How did you do? I ended up with coefficients in the bottom of 2, 11, 18, 9, and 0. The 0 at the end verifies that x minus 2 is in fact a factor. Right here, we're going to go right into the next factor, the x plus 3. If we have x plus 3 as a factor, then we know negative 3 should be plugged in for synthetic division. And guess what? We're going to plug it in right where we left off. So I'm going to create another synthetic division problem and put negative 3 right out in front. And repeat the process again. We'll drop down that lead coefficient of 2, multiply that to the outside, the negative 3, we'd get negative 6. 11 plus negative 6 is positive 5, times the negative 3 on the left, negative 15. 18 plus negative 15 is positive 3. Oh, we're in great shape, you guys. Negative 3 on the outside times 3 would be negative 9. And just like that, we have verified our second factor. Both x minus 2 and x plus 3 are factors for this quartic function. So now to determine what's left over, remember how we follow that process. We know that those coefficients at the bottom represent our answer, or our quotient. The first number after the 0 is always the constant. Then we have our x term as we increase, and our x squared term. Notice all three are positive, so I'm going to put a plus in between the terms on the inside. This means our quotient is 2x squared plus 5x plus 3. This brings us to step 2. To determine the remaining zeros of this polynomial, we need to solve. We have 2x squared plus 5x plus 3. Now, if we set this equal to 0, factoring will be a little bit more of a challenge because of that 2 on the outside. If you're not a fan of the a times c split the b method of factoring, you can always use quadratic formula. I do believe this one will factor, though, if we do a times c. Take the a value and the constant c and multiply them. 2 times 3 is 6. Now, here's where it gets a little dicey. Numbers that go into 6 are 1 and 6, and 2 and 3. Now, both of those pairs in some way can get you positive 5. However, only one pair will multiply to get positive 6 and add to get positive 5 at the same time. That's going to be your positive 2 and your positive 3. Once you know that factor set, we're going to split the b term in the middle. We'll start with our 2x squared, our lead term. And I'm going to split the bx with the 2 and the 3 that we determined by writing plus 2x plus 3x. Together, they would make that 5x up above. And then I'm going to drop down my last term, plus 3. So notice in this step, we didn't factor, we just split the b term in the middle. Now group the first two terms and the last two terms. Our goal is to find a common factor. In the first parenthesis, 2x squared plus 2x, we could take a 2x out of both terms. And that would give us an x plus 1 as a placeholder left over. If we do that again with the next parenthesis, 3x plus 3, we could factor the 3 out of both of those. And once again, we'll have x plus 1 left over. The x plus 1 is a match, and that means it's one of our factors in our final part of this quadratic quotient. To get the other factor, we take the two parts on the outside and we add them together. 2x plus 3. That is the factored form of 2x squared plus 5x plus 3. We're not quite done, though. Remember, we're solving for zeros, so we're still setting this equal to 0. In that first parenthesis, not too bad, we'll subtract 1. X will equal negative 1. That's a real solution. I'm just going to make sure that's an equal sign right there for you. There we go. In the other parenthesis, if we have 2x plus 3 equals 0, we have to do a little bit of detective work. We'll divide both sides by 2, and we get x equals negative 3 halves. So this works out really well for us. We verified that we have x minus 2 and x plus 3 as factors. And our answer would actually be, or our zeros would actually be x equals 2, x equals negative 3. And then over on the right, we also know that x would equal negative 1 and negative 3 halves. This is your lesson for 3.4.